طيب بسم الله الرحمن الرحيم. So last time we started to talk about the theoretical data rates for two cases. For the case of noiseless channel, and we said that in that case the theoretical data rates is actually double the bandwidth in terms of hertz multiplied by log 2 of L, and this is a Nyquist. This does not consider noise on the transmission medium by any chance. Then we discussed the same theoretical limit as well for the case of noisy channel using the Shannon equation, which is B multiplied by log of 1 plus SNR. Okay, so these are the two equations for noiseless channel and for noisy channel. طيب, so once we transmit the signal on the noisy or the noiseless channel, we need to calculate some very important matrix, which is the topic of today's lecture. So we need to discuss the bandwidth, throughput, delay, and finally what we call the bandwidth delay product. The first three are of course have been discussed before in one way or another, and we need to confirm the meaning of, especially for the case of latency and delay, what are the components of the delay and what is the difference between each of these components. That's very important. So to start, we know that the bandwidth can be measured in terms of hertz, and we know that bandwidth in terms of hertz is simply the difference between the maximum frequency and the minimum frequency that can be supported on this transmission medium. So the bandwidth in hertz is the difference between maximum and minimum frequencies. Bandwidth in bits per second, not only does it depend on the bandwidth in hertz, but it also depends on the number of levels, as we have discussed for the case of Nyquist. So the bandwidth in terms of bits per second equals to double the bandwidth, as we said, multiplied by log 2 of L. So it depends. It's directly proportional to the bandwidth in hertz, and it's logarithmically proportional to the number of levels that we can use to represent the bits. So, for example, the bandwidth of a subscriber line is 4 kilohertz of voice. So we know that the voice has a bandwidth of 4 kilohertz. But the bandwidth of this line for data transmission can be up to 56,000 bits per second. So this 56,000 bits per second equals to double the 4,000 kilohertz, or 4 kilohertz multiplied by log 2 of L. Okay, so in order to get this much bits per second on a transmission medium that has a bandwidth of 4 kilohertz, okay, assuming that the telephone line or the voice line has only a bandwidth of 4 kilohertz, actually the typical telephone lines has higher bandwidth than this, but assuming that it has 4 kilohertz bandwidth, then in that case this is the equation, and from this we can calculate the number of levels. Of course, the number of levels here, I think it's 2 to the power 7, which is 128 voltage levels. So if the telephone company wants to improve the quality of the line and increase the bandwidth to 8 kilohertz, what would be the effect on the bandwidth in terms of data rates? So if you double the bandwidth in terms of hertz, you double the data rate directly, because it's directly proportional. Okay. So it's using the same technology, using the same number of levels and everything. If you multiply the bandwidth, you multiply على طول the data rate. So the data rate becomes 112 kilobits per second instead of 56. Okay, واضحة دي? Any questions? So that's the relationship between the bandwidth in terms of hertz and the bandwidth in terms of bits per second. The throughput بقى on the other side is the measure of the actual bits per second that you can transfer at any point of time, which in many cases it varies, and it depends not only on the noise بقى. So the throughput takes into consideration not only the effect of noise, but the effect of noise, the effect of collision, the effect of protocol overhead, many factors that have to be in the picture in order to estimate the actual bits per second that can be sent over the transmission medium. And in fact, this throughput might actually change over time. Why? Because the noise effect changes over time. The probability of collision may change over time depending on the load and so on. So the throughput, the actual throughput or the actual data rates that you can get over the line is definitely less than the bandwidth in bits per second. It's definitely less than the bandwidth, and in many cases it's much less than the bandwidth. So this example, for example, talks about a network with a bandwidth of 10 megabits per second. Okay, but when we actually try to send traffic over this network, we can pass only an average of 12,000 frames per minute. Okay, so 12,000 frames per minute, where each frame is 10,000 bits. So in that case, we multiply the number of frames by the number of bits per frame divided by 60 to get the actual number of bits that we can send over this network per second, which is 2 megabits per second. So when we look at this and we look at the actual, the theoretical bits per second for this transmission medium, it's actually not more than 20%. So the actual bits per second that you can get over the network is sometimes 20% of the theoretical data rates over this network. Okay. So any questions so far? So this is the bandwidth and the throughput, and we discussed this in network 1 before. So this is very important. The latency. The latency is not just one component. It's not only one component of delay. So the best thing to understand the delay, we have actually 4 different components. We have the propagation time, transmission time, queuing time, and processing time. When we say time or delay or latency, all of them are the same. Okay. So what is the difference between all these 4 components? The best thing is to actually visualize the internal process of any node in the network, whether it's a source or it's a switch or it's a router. Okay, so if we look at internally at any node, this node in fact receives the protocol data unit from the upper layers, whether it's a packet or a frame or something. The first thing it does is that it puts this protocol data unit in a queue. Okay, so a switch will store the frames into the buffer, assuming it's a store and forward switch, and it actually stores this in a queue, and the queue, as we all know, is first come first serve. So the first thing that happens to any protocol data unit, like a frame or so, is what we call the Cuen delay. So the best thing to visualize this in real life is to imagine that you are going to the bank. When you go to the bank, you find that the teller is actually busy serving someone, so you have nothing to do but to wait. So to wait in a line, okay, and depending on how much the teller is occupied, you may wait in the line short time or longer time, and that varies during the day. So it's actually, for us, there's no equation deterministic that we can use to calculate the queuing delay. In a way, this is good news for you, because we don't have to go through the actual calculations of this queuing delay. You will get to that when you inshallah, if you decide to study for masters or PhD, you will get to the statistics on how to estimate the average queuing delay and so on. For us here, we just need to know that the queuing time, or the queuing delay, or the queuing latency, is the time needed to wait in the buffer of the output port, okay, until you get to the turn where you have to be served, or you need to be served. So when I wait in the line, whether it's a short time or long time, okay, this is the queuing delay. Once I get my turn to be served by the teller, okay, now I'm in service. I am in service. So now I have the turn to take the service. So once I get my turn for the service, what I do is that what happens is that I need to service that protocol data unit and transmit it over the line. That time depends on the actual width, which is the bandwidth. That time is depending on the bandwidth, and this is the time that takes to process. Actually, this is طبعا processing time هنا. Processing time is the time that I use to read the address where this protocol data unit needs to be sent, whether it's an IP address or a physical address or whatever. And this time is also very low. It's actually negligible. So there's the queuing time and there is the processing time. So now I processed this data frame. I now need to send it over the transmission medium. So sending this is as if I'm actually flowing some water into the pipe. So it depends on the actual amount of water, or the length of the data, and the width of the transmission line. So once I do this, the protocol data unit has become a full signal on the transmission medium. So this time we call it the transmission delay, and this is actually proportional to the length of the data divided by the bandwidth of the transmission medium. So once I do this, I finished transmission of the actual data, okay, and I put it fully on the line. Once I put it on the line, it becomes a signal. A signal it propagates through the transmission line, okay, using the speed, using the propagation speed. So depending on the distance of the transmission line, okay, there's also what we call the propagation delay, which is the distance of the transmission medium, okay, divided by the speed of propagation. واضح كده؟ So the only two components that are deterministically calculated are the transmission latency or delay and the propagation delay. Okay. The other two components are either the processing delay, which is negligible, and the queuing delay, which can be estimated statistically based on so many factors, and as we said, we will not get to that. واضح كده يا شباب? So these are the four components of the delay, which are very important. طيب. So if the propagation time across the line between 2 points is actually a 2 points distance apart by 12,000 kilometers, we have the propagation speed of 2.4 times 10 to the power 8, which is slightly less than the speed of light. So in that case, the propagation time or the propagation delay is nothing but 12,000 multiplied by 1,000 to convert it to meter, divided by the speed, which is 2.4 times 10 to the power 8, which is 50 millisecond. 50 millisecond in networks is significantly high, and that's because of the fact that the transmission line or the distance between the 2 points is actually extremely large. So this is a distance of like under marine cable or something. So this is huge. And that's why the propagation time is significant. 50 millisecond is actually significant. So when we go to the Atlantic Ocean, the propagation time becomes significant. This is unlike, for example, if we're talking about a small land covering a lab or covering a building. Okay, so in that case, of course, this distance is extremely high, and in the case of a building or a lab, we're talking about few meters, in which case this propagation time is actually negligible or very low. So when we talk about lands, we usually neglect the propagation time, but as we will see, the transmission time for the case of the lands becomes the more dominant factor. For the case of undermarine cables, usually we use very, very high bandwidth because we have to use fiber optics. Okay, so in that case, the bandwidth of the transmission line is very high, which means that the transmission time is very low. Okay, but the propagation time is significant because of the very large distance. Okay, واضح كده يا شباب? Any questions so far? So this is the case of a propagation time for the case of very large bandwidth. So for the case of very large bandwidth, if we need to send a data of length 2.5 kilobyte, okay, which is like an email or something, we need to send it over a transmission medium of a bandwidth 1 gigabits per second. So in that case, the bandwidth is extremely high, and in that case the propagation time as we calculated is 50 milliseconds, still the same, and the transmission time becomes the length here is 2.5 times 1000 times 8, because this is a kilobyte. So if we multiply it by 1000, we convert the kilo to byte, and then times 8 to convert it to bits. Okay, so just pay attention to the units. So this becomes 2500 multiplied by 8 in terms of bits, divided by, of course, the bandwidth of the line, which is 1 gigabits per second, which is 10 to the power 9. So the transmission time becomes 0.02 milliseconds. So if we look at this and this, of course, this is negligible. Okay, so in that case, the transmission time becomes very negligible, and that's typically the scenario for undermarine cable, where the distance is very large, but the transmission delay is very low. Okay. So if we take the same transmission line or less in terms of distance, and we make the bandwidth very low, which is typically بقى ايه the case for مثلا LANs, for the case of Ethernet. Here طبعا of course it's extreme. Ethernet يعني in the range of 100 megabits per second or something. Then the transmission time becomes a 40 seconds compared to طبعا 50 millisecond. Then this one is more dominant. In which case the transmission time becomes more dominant compared to the propagation time, and that's more in the scenario of the LANs, where the bandwidth is low, and usually even the medium is low in terms of distance. The last component here is what we call the bandwidth delay product. The bandwidth delay product is nothing but the bandwidth multiplied by the delay. The bandwidth in terms of bits per second, okay, multiplied by the delay in terms of second. So if we say that this is a bits divided by second multiplied by second. So what is the unit for the bandwidth delay product, يا شباب? What is the unit for the bandwidth delay product? Bits. So this is bits. Okay. So what is the actual meaning of this? The bandwidth delay product represents the amount of burst or the amount of bits that can fill the transmission medium. Okay. So by the time you finish the transmission for one full unit, what is the actual number of bits that you have sent? All right. So so this is the bandwidth delay product. So for a full duplex channel معناها ايه؟ معناها you have concurrently the transmission happening in both directions at the same time. So in both directions at the same time, in that case, the bandwidth delay product becomes 2 times the bandwidth times the delay, because we're talking about full duplex transmission. Full duplex transmission معناها 2 nodes, each of them are sending and receiving at the same time. Okay, so if we have 1 bit being transmitted, the bits per second constitutes the bandwidth in terms of bits per second. All right. So the delay gives me an indication of the amount of bits that I can use to have one full burst, okay, on the line. And if the transmission time or the delay time represents the length of the burst, okay, and the bandwidth represents the width of the pipe, then the bandwidth delay product is nothing but the volume, the amount of bits that can fill all these transmission medium. Okay, so visually the bandwidth delay product is actually the volume of bits that can fill the transmission medium. Okay, so bandwidth delay product is not a very common metric. The more common metrics are the first 3 that we talked about: the bandwidth, the throughput, and the delay component. And for the delay, we particularly focus on transmission delay and propagation delay. Okay, so this is the bandwidth delay product, which constitutes the volume of bits that can fill the transmission medium. Anyone has a question? Any questions? I see someone raised his hand and then he... Yes, Daniel, go ahead. Right. This one is for the whole burst. Yes, the whole burst that fills the line. Yes, the whole burst that fills the line. So this is actually the amount of bits that can fill the line, which is the delay multiplied by the bandwidth. Okay. Yes, the transmission delay. Yes, the transmission delay. Yes. Okay, so this is actually the end of this chapter, data and signals. This was actually the foundation for the properties of the signals. We talked about the properties of the analog signals, the properties of the digital signals, the two types of transmission, which is baseband transmission and broadband transmission. For baseband transmission, we said that we take the digital signal, which has fixed duration, fixed voltage level in a duration of time. We transfer this digital signal over the line as is, and this is actually what we will talk about in chapter 4 more in details. There's the broadband transmission, where we have to convert the digital signal to analog using a high frequency carrier, okay, and we use that to first align the properties of the transmitted signal with the properties of the transmission medium, because as we said, the transmission medium itself has a bandpass effect, right? And at the same time avoid the infinite frequency components of the digital signals, which requires some approximation. So in chapter 4, we start to talk about this particular phenomena of digital transmission. By digital transmission here, we mean that we take the actual digital data, of course, our data is in that case digital, ones and zeros. We talk about ones and zeros. And we convert it to a digital signal, which can be transmitted as is over the line. Okay? So this is what we need to talk about in this, or in other words, we talk here about the baseband transmission. In the baseband transmission, we have very important characteristics that we need to talk about, including the line coding and line coding schemes. What line coding is, okay? What are the line coding schemes? We talked about two examples of line coding schemes in network 1, which we will talk about again now. And then we talk about the concept of block coding and scrambling. Okay, so all of these techniques and definitions are valid when we talk about digital to digital. By digital here, we mean digital data to digital signal. Okay, by digital data to digital signal, and this digital signal will be sent over the transmission medium as is, which means that we're talking here about baseband transmission. Okay, so what is the line coding? Line coding talks about the fact that we take the actual digital data here, and we need to convert this digital data to a digital signal. Okay, which means that in order for us to do that, we need to map some data element to a signal element. By data element here, we mean what is the data unit that we're talking about, whether it's 1 bit, maybe 2 bits, okay, and how to map this to a signal element. A signal element is a fixed, because we're talking here about digital signal. A signal element is a fixed voltage level in a duration of time. A fixed voltage level in a duration of time. That's what we mean by signal element. Okay, طيب. When we do this, the simplest form that we talked about in network 1 يا شباب was ايه بقى؟ اللي هو non-return to zero. For non-return to zero, we simply talk about stream of bits like this. Okay, and each single bit, it gets mapped to one data element. صح? Right? So this is in fact a the simplest form where we have one data element gets mapped to one signal element. Okay? Can we have one data element represented by two signal elements? And what is the actual example of this? Give me an actual example of this. If it's true, yeah. Yes, Daniel. Okay. Yes. So we have, like, for example, the 0 is like this, and the 1 is like this, right? So this is in fact two signal elements, to represent the same bit. Okay. So we'll see today why do we need to do this. Of course, we talked about it in Network 1 before, but today we will understand it even more. And we'll talk about more phenomena that will make this really more appreciated. So that's definitely true. So you have two signal elements to represent the same bit. Can we have the other way around? Can we have two bits represented by one signal element? Yes, we can have that. In fact, we talked about the general case from Nyquist when we said that we have the maximum data rate is actually double the bandwidth multiplied by log 2 of L. So each of these voltage levels is one signal element, but if we have multiple of these, we can use multiple voltage levels to represent 2 bits or 3 bits or 4 bits and so on. Right? So if we need to represent 2 bits using one signal element, then we need to have 4 different signal elements, 4 different voltage levels. If we need to have 3 bits represented by voltage levels, then or signal element, then we need to have 8 different signal elements to represent 3-bit patterns, and so on. Right? So this is the general case. Type. This is the relationship between the data element and the signal element. So here, for example, we have the simplest form, which is the non-return to zero polar, as we will talk about it in a minute. So here we have one data element represented by one signal element. Okay, so in that case, we have the R ratio. The R ratio is the ratio between the data elements to the signal elements. Data elements to the signal elements. So number of data elements that can be represented by a signal element is 1 to 1, which means that R is 1. Okay, so for the Manchester encoding, we have the 1 is represented by 2 different signal elements. Okay, 2 different voltage levels to represent the 1. So in that case, we have 1 data element by 2, so R is half. Okay, for the other way around, we have 2 different bits represented by 1 signal element. So in that case, of course, we need to have 4 different signal elements, but each one represent 2 bits. So in that case, R is 2 simply, and this is the arbitrary form. The arbitrary form here, you can have whatever combination you want. So here we have 3 different signal elements to represent 4 different bits, and we will talk about why do we need to do this later on. So in that case, R is the number of data elements divided by the number of signal elements. So it's 4 over 3. Okay? Any question, ya shabab? So R here is the ratio between the data elements to the signal elements. ماشي؟ طيب, so how do we characterize the line coding schemes? We characterize the line coding schemes by the actual data rate. The actual data rate here is n. We know that. Okay, so the actual data rate, which is the number of data elements, okay, the number of bits يعني, that we need to send per 1 second. Okay, طيب. So that's well known. We know that this is the number of bits per second that we need to send. We have a new sort of a new component, which is يعني we talked about it in a way, which is the signal rate. Sometimes we call it the baud rate, sometimes we call it the pulse rate, sometimes we call it the modulation rate. All of these are names for the same thing: signal rate, baud rate, pulse rate, modulation rate. All of them are the same, okay? Which is the number of signal elements. And I need to change this slightly here and say changes in 1 second. So this definition cannot be just يعني number of signal elements in 1 second and that's it. We have to measure the change of the signal element. So it's not by the number of signal elements per second. It's actually the change of the number. And the best example of this is the signal rate is actually is proportional to the frequency of the digital signal. The frequency of the digital signal. So if, of course, we know that the highest frequency of the digital signal is infinity. We know that, but again, we also discussed the fact that we can approximate this digital signal using some analog signals. صح يا شباب? We talked about this. So if we talk about a signal in the time domain, and this signal is is actually a digital signal that represents 1111111. Okay, so if we use non-return to zero in the roughest form, so this signal is nothing but fixed signal like this. Okay, so what is the frequency of this signal? It's actually zero. صح? The frequency of this signal is zero. What is the number of signal elements per second? So S here is n. صح? Number of signal elements per second is the number of bits per second. صح? But actually, if we stick to this rate, if we stick to this definition like this, then the number of signal elements is equal to the number of data elements, which is n. Okay. However, the signal rate is proportional to the frequency of the signal. Okay, which in that case is actually zero. Okay, so this is an extreme example. So the signal rate is the number of signal element change per second. Is the number of signal element change per second, and this is very important. Is the rate of change in the digital signal per second. Type. So an example. So a signal is carrying data in which one data element is encoded as one signal element. So R is 1. طبعا we know that. If the bit rate is 100 kilobits per second, what is the signal rate or the baud rate? Well, we talk about a very important يعني parameter here, which is called the case factor. The signal rate is proportional to the bit rate, okay, and proportional to 1 over R طبعا. So in other words, the 1 over R is the rate of data elements divided by, sorry, the rate of signal elements divided by the data elements. يعني how many signal elements, right, we use to represent the data elements. So the more signal elements, okay, we use to represent the data elements, the higher the signal rate or the frequency. صح كده? So 1 over R here means the rate of signal elements divided by the data elements. And the more signal elements we use to represent the same data elements, the higher the signal rate or the frequency. So that makes sense. What is this case factor? The case factor here is constant. Okay, is a constant factor which represents the statistical patterns of the signal. So in simple term يا شباب عشان ما حدش يتلخبط يعني, in simple term, case factor is given. Case factor is given, and in many cases it's actually 1 over 2. You can assume that at any point of time during this chapter, if the case factor is not there, you can assume it's half. على طول. The case factor is half. In reality, what does this case factor represent? This case factor, in fact, represents the the statistical property, the statistical probability, okay, of having the changes of the signals, okay, during a specific time. So, for example, if we're talking about ones and zeros like this for the case of non-return to zero, okay, so if we have all straight ones all the time, as we said, the signal rate is actually zero. Okay, so what is the probability of having this? What is the probability of having 1 and then 0 and then 1 and then 0 and then 1 and so? This is the worst case, right? So the worst case here is to have the 1 as positive and the 0 as 0. 1 is positive and the 0 as 0 and so on. And in that case, we have the highest signal rate. Okay, so what is the probability of having all ones? What is the probability of having all zeros? What is the probability of having ones and zeros and so on? All of this is actually summarized in the case factor. Okay, so the case factor here represents the statistical pattern of the bits or the digital bits, and in many cases it's half. So if we assume that the case factor is half, okay, for a signal that has digital bits that have a rate of 100 kilobits per second, what is the average value of the baud rate or the signal rate or the modulation rate? It's actually a C, which is half, multiplied by the N, okay, multiplied by 1 over R, which is 1. So this is a 50 baud rate. In fact, this is the roughest and this is the minimum bandwidth. This is the minimum bandwidth or the minimum amount of signal rate that we need to represent these bit rates. This is the minimum. Okay. جبت الكلام ده انا منين بقى؟ شايف هنا ايه؟ This is a 800 kilobits per second, and this is the bandwidth or the amount of signal rate is half the data rate. Where did we see this before, يا شباب? Why do I say that this is eh? Why do I say that this is the minimum? Eh? لا this is good. This is actually non-return to zero. I didn't hear. What do you say? Okay. Okay. Yes. Not throughput. No. There's no throughput here. All of this is just theoretical estimations. There's no actual here. We're talking here about the theoretical limits in terms of bandwidth and bits per second. So what is the relation? Okay, so this is actually based on Nyquist, Shara. This is based on the Nyquist, where we said that the actual bandwidth is half the data rate. This is the minimum bandwidth that you need to transfer using طبعا the roughest approximation, because this is using the roughest approximation. So if we have a specific data rate, so the minimum bandwidth that we need to represent this data rate is half the data rate. Okay, so this is based on the Nyquist theory. So in that case, the bandwidth is actually the signal element. The minimum bandwidth is actually the signal rate. Sorry, the signal rate, which is S. Okay. So talk about the baud rate. Okay. The baud rate determines the required bandwidth of the digital signal. The baud rate determines the required bandwidth, which is the rate of changes. Okay, so the bandwidth is proportional to the rate of changes in that digital element. So so the bandwidth is proportional to the signal rate. So which means that the minimum bandwidth required is actually the case factor multiplied by n multiplied by 1 over r. 1 over r, as I said, is the rate of signal elements divided by data elements. Okay, so the more signal elements I use to represent the same data elements, the higher the bandwidth required. And that's why when we talked in Network 1, we said about the Manchester encoding. We said that Manchester encoding was good in many ways, but what is the cost that I had to pay? More bandwidth, right? More bandwidth, because here 1 over r is 2, okay, which means that r is half, 1 over r is 2, so which means that I had to spend double the bandwidth. I had to spend double the bandwidth in order to represent the same data rate. But of course, there are some other advantages that I gained by doing this, and we will talk about it again now. So if I have a specific bandwidth, if I have a transmission medium, okay, with a specific bandwidth in terms of hertz, okay. Now, what is the maximum bit rate? It's actually 1 over C multiplied by that bandwidth multiplied by R, okay, which is the reverse, okay. So if I have a specific bandwidth, the maximum data rate I can inject in that bandwidth using the digital transmission is 1 over C multiplied by the bandwidth multiplied by R. Okay. طيب. So before we talk about the line coding schemes, we need to talk about a very important phenomenon that we have in digital transmission. One of them is the effect of lack of synchronization. Effect of lack of synchronization. So remember, Shabab, the lack of synchronization, this is a phenomenon that we suffer from whenever we have two nodes using طبعا separate hardware circuits to generate their synchronization clocks. Okay, so here I have two clocks. So even if I have the same frequency and the same values to generate these clocks, due to the hardware impairments, these clocks, they suffer from a very physical phenomena, which is the clock drift. Okay, so physically كده these clocks, they cannot be 100% identical. Okay, so these two nodes, let it be any two nodes in the network, switch and router, source and destination, whatever. The problem here is that these clocks are not identical 100%, which means that if I have here, this is a source and this is a destination, there's a chance that the destination clock will inevitably have a duration for the bit which is less or more طبعا compared to the duration of the bit at the source level. Okay, remember, what for digital transmission, what is our objective? Our objective at the receiver is two things. Remember, this is very key. One, determine the bit boundaries correctly. Okay. Two, within 1 bit duration, estimate the voltage level. Okay, so these are the two objectives. So at the receiver, if the ideal case is that at the receiver, when I receive a signal like this, okay, I say, okay, I can detect the bit boundaries here exactly, okay, and within this bit duration, it seems that the voltage level is positive, so this is 1. And here it seems that the voltage level is negative, so this is 0, and so on. And I was able to recognize all the bits correctly. So if I can detect the bit boundaries correctly, and within each bit boundary, within each bit duration, I can detect the voltage level correctly, then my job is 100% correct. Okay? But of course, live is not that easy. Live is not that easy. So on the first objective here, so for the first objective here, you have the challenge of a clock drift. So instead of being able to detect the bit durations correctly, the receiver or the destination, unfortunately, has a clock that's a little bit faster, just a little bit faster. Okay? So what is the effect of lack of synchronization? Well, it's drastic. It's drastic. Let's see. So here, the receiver will say, oh, okay, so here the bit duration is positive. Within this bit duration, the voltage level is positive. Okay? So this is 1. What is the bit here? I really don't know. I have some high voltage and some low voltage. Okay? So what is this bit? I don't know. Okay? Let alone that here, because of the fact that the clock duration is faster, or the clock frequency is faster a little bit, I was able to detect higher number of bits, more than what I really transferred. واضح? Because of the fact that the clock at the receiver side is faster, I detected more bits than I really sent. Maggie, do you have any questions? تفضل يا Maggie. Yes, so as I said, these are two nodes in the network. This is the source and this is the destination. Whenever I have any two nodes in reality كده, trying to coordinate the same thing, using or synchronizing themselves to do one يعني job, which in our case here is to transmit some bits and get it on the other side. Okay, these two nodes physically, they do not have identical clocks by any means. Even if you try to make the properties here and here the same to generate the clock, they will not have 100% identical clocks. Why? Because of the hardware impairments. The hardware circuit itself, in terms of يعني they use some crystal بتاع ده يعني objects to generate that frequency. These have some hardware limitations. So the clocks are not the same. So we have what we call clock drift. So clock drift here means that the clock at the receiver side is not 100% synchronized with the clock at the sender side. What is the effect of this? The effect of this is twofold. One, you try to detect more bits than what you really sent. Okay, because here the bit duration is shorter, which means that the number of bits that I have seen in the signal is more than what the signal actually contains. Okay. Two, I detected many bits in error because here the bit, during that bit duration, the voltage level is actually very confusing. So how would I know whether this is 1 or 0? I don't know. Okay, so in many cases it's very confusing to the receiver. So the lack of synchronization is a very key, critical phenomenon that happen in digital communication, which is because of the fact that the clock at the source and the destinations, they are not synchronized. Okay, طيب, we talked about this problem as well. Okay, so not only does it cause extra bits, some of that, again, you have here clock durations. The clock duration at the receiver side is a shorter, which means that this clock is faster. Okay, so see some example to make this clearer. So in a digital transmission, the receiver clock is 0.1%. خد بالك, 0.1% faster than the sender. How many extra bits per second does the receiver receive if the data rate is 1 kilobits per second? 1 kilobits per second and 1000 bits per second. Remember, 0.1%, this means 0.001, right? Which means that for each 1000 bits, I have 1 bit extra. Okay? So for each 1000 bits, I have 1.1. Or in other words, you can multiply the number of bits that you send by n multiplied by 1.001 to know how many extra bits you have. Okay? Because this is 0.1%. 0.1% divided by 100, which is 0.001. Okay? So so if you send n bits, you get the n bits plus 0.001 of these bits. So for each 1000 bits, you have 1 extra bit. That makes it 1001. Not only that, these 1001 bits, by the way, it's very challenging to detect them correctly due to the bits will not be detected correctly. أيوة ميجا. Yes, هو بالضبط الاكسترا بيتس دي are due to the clock drift. Yes. Yes, yes, these extra bits are because of the clock drift, because of the fact that the two clocks at the sender and the receiver, they are not 100% identical. No matter what you do, they are not 100% identical. So because of this, you have some extra bits that the receiver will see, okay, even though the sender did not actually send these extra bits. Because of so these extra bits have not been sent by the sender, but the receiver still sees them. And not only that, these actually cause the receiver to detect some errors in the bits, and we will see that again. So if we send 1 megabits per second, we have 1000 extra bits. So can you imagine? This is 1 million bits, by the way, is a small file. You are sending an email مثلا ولا حاجة 1 megabits per second, let's say an attachment مثلا small file أو كده, you get 1 megabits. So for 1 megabits you get 1000 extra bits. This is significant, which means in a way that this clock drift or this lack of synchronization issue needs to be solved. It needs to be resolved. It exists and it's limited by physics. We cannot do anything about it. We try to perfect the hardware circuit as much as we can, but still it's there. Okay, so how can we solve it? So our tool to solve the lack of synchronization is through the digital signal itself that we are sending, and we will see how this is done. So in order to characterize, or in order to know the pros and cons of any line coding schemes, we did not talk about line coding schemes yet. We will start to talk about them next time. We have a very, very important three phenomena. Baseline wandering, and I will talk about this as the second one, and then the third one. One and two here, they correspond to the two objectives I talked about. The two objectives at the receiver: to, one, detect the bit boundaries correctly; two, within each bit duration, detect the voltage level correctly. Okay, so let's talk about each one quickly. So if I have an unreturned to zero, this is the simplest. We keep using that because it's the simplest. If I have 1 and then 0 and then 1 and so on, and then 1 مثلا, so the signal, the digital signal, looks like this. Okay. طيب, assuming, and I will talk about the otherwise, but assuming that I detect the bit boundaries correctly now, for now okay, what do I do at the receiver to detect that this is 1 and this is 0? What I normally do at the receiver side is to use a voltage comparator. Okay, I use what they call a baseline. A baseline like this. We call this a baseline. Okay, I use a baseline, and طبعا for the case of positive voltage and zero voltage, the best baseline is يا شباب naturally is to put it somewhere in the middle. صح? Put the baseline somewhere in the middle. Anything below the baseline, I will assume it's a 0. Anything above the baseline, I will assume it's 1. صح? Very easy. So that's what I normally do at the receiver side. So the baseline, if I fix the baseline in the middle, this would be the best. But again, life is not that easy. Why? Because I neglected here the effect of the noise completely. Here, I neglected completely the effect of the noise. One of the important effects of the noise is what we call the bias signal. بمعنى إيه؟ the noise gives the signal, the digital signal, a push in the voltage level, up or down. Okay? So this is one of the effects of the noise. It pushes the signal level up or down. So instead of receiving a signal that looks like this black signal, I receive a signal that looks like this. Okay? So in that case, the noise has given me a push lower. Okay? Which will make this fixed baseline, the baseline now becomes a little bit inaccurate. So if the noise pushes the signal a little bit lower, it might cause errors in detecting the voltage level at each bit duration. واضح كده يا شباب؟ واضح so far? So the bias that the noise causes to the signal might confuse the baseline to detect the bits in error. So what do I do? What they normally do at the receiver is to use a variable baseline. A variable baseline. So this baseline is not fixed anymore. It's variable. The variable based on what? They use a baseline which is variable to the moving average of the signal. The moving average of the signal itself. So the digital signal itself, okay, represents or controls how the baseline is actually chosen at the receiver. So if, for example, مثلا, if I assume that I have 1, 1, 1, 1, 1, okay, so this will make the signal look like this, fixed. So at the receiver side, the receiver will say, oh, okay, so I received a high voltage level, so in that case, the baseline starts to increase. Once I get, like, for example, a 0, then the baseline will fix a little bit, and then it may go down or it may go up and so on. So statistically, by using variable baseline like this, we lower the probability of error in detecting the voltage level of the signal. Okay, so by using a baseline based on the moving average of the digital signal itself, we reduce the errors. طيب ماشي، فين بقى البروبلم بقى؟ What is the problem actually? The problem is that we have what we call baseline wandering. Baseline wandering. The baseline wandering here talks about the fact that if the digital signal stays at the same level for a long period of time, like for this extreme case, ya shabab, when I have all ones, okay, what will happen is that the baseline will start to increase, and get as close as possible to the actual signal level. طيب ايه المشكلة؟ المشكلة ان انا if I receive 0 afterwards, I will not be able to detect this 0. Okay? Because this 0 will cause the actual signal level to drop, and the baseline is high. So in that case, I may detect the actual ones later on in error. So in other words, yani, we should not have the same level of voltage for a long period of time. This is bad. This is really bad. Any digital signal that has the same voltage level for a long period of time, that's really bad. Why? Because of the fact that it causes baseline to wander up or down for a long period of time, and that increases the probability of error in detecting the voltage level. Okay, so that's what we mean by baseline wandering. Baseline wandering, when we have the same voltage level for a long period of time, the baseline starts to go up for a long period or go down for a long period. ماشي? The other يعني problem, which is again it exists if I have the same voltage level for a long duration of time, is the synchronization, lack of synchronization. If I have the same voltage level for a long period of time, okay, then I do not have any information in the signal that tells me where the bit boundary is. But if I change, like for example for the Manchester encoding, if I change the bit level, if I change the voltage level for the same bit, then the receiver would know that there is a change here, and I know that this change happens in the middle of the bit. So I can use this information to synchronize my clock, which is what we call self-synchronization. So my tool to try to synchronize myself back at the receiver side is the digital signal itself, the change in the digital signal itself. So the more changes I have, okay, the more accuracy at the receiver side in resynchronizing its clock. Therefore, reduce the probability of error, reduce the probability of receiving extra bits than what has really been sent. So, in other words, the rule of thumb here is that you should never have the same voltage level for a long duration of time. This causes these two problems. Baseline will wander up or wander down, okay? And at the same time, you will not have any change in the signal that will allow the receiver to synchronize its clock. واضح? So this is the rule of thumb. You should never have the same voltage level for a long period of time. سواء positive أو negative أو zero. Positive أو negative أو zero. Okay? So if it's zero for a long period of time, it will cause these two problems. baseline wandering, and the lack of synchronization. If you have positive, same thing. If you have negative, same thing. طيب, what is بقى the final one, which is the DC component? DC component here, the best thing to understand it is to look at the frequency domain, not the time domain. If the digital signal has a high power at zero frequency, يعني it has a bandwidth that looks like this, this one is really bad. Why? If it has high power at zero frequency, this is bad. Why? Because physically, at the receiver side, we use typically low pass filters. صح? We use low pass filters to get this signal, as we have discussed before. The problem with this is that any low pass filter will have a bandwidth that looks like this. Okay? It always starts from a low power at low frequency. So generating a low pass filter that looks ideal like this, it's not possible in practice. It's not possible. So in all cases, these components will be distorted from the signal. Will be very distorted from the signal. So it's always not advisable to have high power at zero frequency. High power at zero frequency. So this is what we call a DC component. A DC component talks about high power at very low frequency. So as we said, مثلا our voice has a bandwidth of 4 kilohertz. صح? We said that our voice has 4 kilohertz. So we need to use a low pass filter with a bandwidth of 4 kilohertz. However, if you do this, you discover that any voice components below 200 hertz is not easily heard, or it's not easily detectable. Type, when do we have a DC component? When do we have a DC component? So if we have a signal, a digital signal that has positive voltage, which is equal voltage, the same fixed level of voltage for a long duration of time. What is the frequency of this signal, يا شباب? What is the frequency of this? 0. Right. What is the power? Because the voltage level is positive, the power is actually V square. The power is the V square. Right? So this is what we call a DC component. So again, you should never have a fixed positive voltage for a long duration of time. Type, what if we have zero voltage? If we have zero voltage, is this a DC component? No. Why? Why? Because there's no power, because V here is 0, so V square is 0. V square is 0. So in that case, we do not have a DC component. So again, so it's always advisable to have no positive or negative. طبعا, if you have negative, it's the same because it's V square. Huh? Remember, the power is V square. So ولا positive ولا negative for fixed voltage for a long duration of time, because this causes a DC component. If it's 0, it's fine. If it's 0, it's okay, because this is no power. واضح? So in all cases, it's very advisable to change the voltage level, preferably within the same bit. Within the same bit, it's preferable to use multiple voltage level, because this allows us to eliminate the baseline wandering. It allows us to have self-synchronization. Okay, and if we have alternating voltage levels like this, we will not have any DC component. Okay, so these are the three phenomena. Based on these three phenomena, we will characterize by all the line coding schemes starting from next time, inshallah. Okay.